Okay, now the recording should be happening. Okay, let's do it again. Hi everyone. My name's Alex. Today I'm gonna talk about online algorithms for spectral hypergraph sparsification. This is joint work with Tasuku Soma and Yuichi Yoshida. Okay, so I'm gonna start by introducing the problem. So um, let's talk about graph sparsification. Let's say you're given a graph G. And basically, it's a very well motivated problem. The goal of sparsifying the graph is to reduce the size to speed up downstream algorithms. So while reducing the size, you change the graph. Some aspects of the graph will not be captured, but we still hope to approximately preserve certain properties of the graph. So if we want to preserve shortest paths, then we get the notion of spanners. If we want to preserve cuts or spectrum, then we get respectively cut and spectral sparsifiers. And there are also many other possibilities depending on what you want to preserve. So for ordinary graphs, cut sparsification means you want to approximately preserve the cut values. So basically, or in the original graph G, there's a weight W on each edge. And then you want to find a new set of weights, W tilde. The weights are non-negative. And then we say that the new graph G tilde is an epsilon cut sparsifier of G if the new cut value across all cuts is within 1 plus minus epsilon of the old cut value um, across the cut S. So the cut value across S is simply the sum of edge weights, basically across the subset. In the diagram here is basically the sum of the red edges. And so this means that the cut values are approximately preserved. And then we also want the number of edges in G tilde to be small. And then spectral sparsification of graphs is a notion first introduced by Swiman and Tang in 2011. So basically, instead of looking at cuts, they try to preserve the spectrum of the Laplacian. So for the purpose of this talk, we look at the quadratic form. So if the quadratic form of the Laplacian at x is, so you sum over all the edges uv, and then for each edge uv, um, the contribution to the quadratic form is the weight times the squared difference of the vector x at points u and v. So just the formula here in the second line. So we say that the new graph G tilde is an epsilon spectral sparsifier of G if the quadratic form is within 1 plus minus epsilon of the old one for all vectors x. So one important feature of this definition is that spectral sparsifier is cut sparsifier because when you plug in the characteristic vector of a subset S to be a vector X, then you can check that X transpose Lx, the quadratic form, is exactly equal to the cut value of S. There have been many results on how to find a spectral sparsifier. Roughly speaking, there are like three classes of approaches. So one is based on decomposing the graph into like well-connected components with very few edges in between. And then the second one, sampling based, basically assigning a probability to each edge and then sampling them with that probability. And actually the optimal number of edges is obtained using like potential function based approaches. So basically using some sort of potential function to guide your decision on like which edge to include. And there are many applications for spectral sparsification of graphs, including Laplacian solvers, flow algorithms, cut algorithms, clustering, sampling spanning trees, and so on. So this is all about graphs. And before we move on to hypergraphs, are there any questions so far? Okay, so let's move on to hypergraphs. The difference between hypergraphs and graphs is basically now edges are replaced by hyperedges. So edges, you can think of it as subset of two vertices, and hyperedges is subset of any vertices. So for hypergraph, the cut value is defined as, so first of all, a hyperedge is cut by a subset S if there's some part of it inside S and there's some part of it outside of S. So basically, you can look at the diagram on the right, and it's if those boxes are the hyperedges and the dotted circle is the cut, then the two red hyperedges are the ones cut. And the cut value is simply the sum of the weights of the red hyperedges. So with this, we can again define epsilon cut sparsifier. And the tricky thing here is that the cut function here is not really a quadratic form in the graph, like in the same sense as in the graph case. So for this, Soma and Yoshida, they defined hypergraph energy, or like quote unquote quadratic form, to be this QH of X. So again, it's a sum over hyperedges. And for each hyperedge little e, the contribution now is weight times the maximum squared difference between the xu's in the hyperedge. So with this notion, you can define epsilon spectral sparsifier of hypergraphs to simply be to find an H tilde so that the energy at each point x is within 1 plus minus epsilon of the energy for the original graph H. So once again, this definition has the nice property that spectral sparsifier is cut sparsifier. Because when you plug in x to be the characteristic vector of S, then you can see that for each hyperedge, the energy is 0 if the hyperedge is not cut, and it's WE if it is cut. So when you sum them up, you just get the cut value. So for hypergraph sparsification, there are a lot of results. So most of them are sampling based. I just want to highlight two of them. So the best cut sparsifier result is by Chen, Kana, and Nagda. The number of hyperedges is actually n log n divided by epsilon squared. This is the same as the best sampling-based graph sparsification results by Swiman and Srivastava. And then for spectral sparsifier, recent results by Lee and also Jabalapati, Liu, Sifid, they obtain basically just with a log R factor extra, where R is the rank of the hypergraph. So one issue here is that all these algorithms are offline. So that means in order to compute the sparsifier, they need to first read in the entire hypergraph. And for hypergraphs, this could be an issue because just the number of hyperedges, m, can be exponential in the number of vertices. So that means it could be expensive simply to store the hypergraph. So one goal here is to devise an algorithm for spectral sparsifier without having to see all the hyperedges. So that's why we consider the online setting. So in the online setting, the hyperedges EI with their weight WI, they arrive one by one. And when it arrives, the algorithm decides immediately, sorry, whether or not to include the hyperedge and also to assign a new weight W tilde I if applicable. And the task is to find a spectral sparsifier of the given hypergraph using just poly n working memory and its number of vertices. So this is the result we obtain. Um, so to describe this result, we need to relax the definition of spectral sparsifier a little bit. So basically the difference is now we have epsilon and delta. So epsilon is the multiplicative error for the energy, and delta you can think of it as an additive error. And what we obtain is that there is an online algorithm that computes an epsilon delta spectral sparsifier with this many hyperedges with high probability, and then the working memory is just O n squared. So to better interpret these results, let's consider just one special case. So we can show that as a corollary, let's say if the hypergraph is R uniform, so each hyperedge is size R, and if it's unweighted, then basically this translates to nr log squared and log r divided by epsilon squared hyperedges. So you can see that there's an extra linear effect of R, and also the log n if you compare it to the best spectral hypergraph sparsifier by Lee. And also, this algorithm is based on like a sampling regime. So are there any questions so far? Okay. So I'm gonna describe some past work about like sampling-based sparsification algorithms before describing our algorithm. So again, let's go back to ordinary graphs. Um, the most well-known sampling-based algorithm is based on the so-called effective resistance of an edge in the graph. So basically, we compute the effective resistance, RE, which has this form, and then we just sample the graph edges independently with probability proportional to the effective resistance. So there's an extra factor C here, which is an oversampling rate. It is necessary to guarantee spectral sparsification. And then once you sample the edge, the new weight W2 of E is basically just WE divided by PE. So it's a natural choice because then you guarantee that the Laplacian of the sparsifier, so L tilde, is unbiased. And then if you use matrix Chernoff, you can show that when you choose the oversampling rate to be log n divided by epsilon squared, then you obtain an epsilon spectral sparsifier with high probability. And then finally, the expected number of edges would just be the sum of the PE, which is basically the oversampling rate times the sum of effective resistances. And it's a nice fact that the sum of effective resistance is O of n. So that's why the expected number of edges is O of n log n divided by epsilon squared. And then finally, you can use Chernoff to show that the sparsifier has this many edges with high probability. So actually, effective resistance sampling belongs to a more general class of algorithms called importance sampling or leverage score sampling. It's because you can think of it as measuring the importance of the edge in its contribution to the quadratic form. So you can write the effective resistance as the maximum contribution of edge energy to the overall energy. And so this idea can be taken to hyperedges. We're actually not going to use this directly because it's not easy to compute this. But then conceptually, this is important to know that the notion of importance is can be similarly defined for hypergraphs as just the maximum fraction between the energy at a particular hyperedge E and the overall energy. Okay, so to go from graphs to hypergraphs, to drastically reduce the number of hyperedges in the sparsifier, one important idea is the clique graph reweighting. So basically, for each hyperedge H, so like in the left, you replace it with a clique on those vertices. So like the clique on the right. So you do that for each hyperedge, then you obtain this multigraph G. So it's an ordinary graph, but there can be like repeated edges, parallel edges. So this lemma by Karpelov, Krautgamma, Tardosh, and Yoshida, and also by Lee, it says that there exists a choice of edge weights, C, E, U, V. So you can think of it as assigning a weight to each edge in the clique graph. So first of all, the first property says that, the first property says that the sum of the edge weights for fixed E is equal to the weight of the hyperedge. And the second one says that it only assigns weights to edges in the clique graph with the maximum effective resistance in the hyperedge. So this is a little bit, perhaps a little bit hard to digest, but basically just keep in mind that we find a special set of weights on the clique graph. And then here the message is basically that these weights, which will be useful, they can be found using convex optimization, in particular in
Sorry,
point
Alex,
limit.
what is
Yeah.
the R? Can you go back to the definition of R? Sorry, I
Oh
forgot what
yeah.
it is.
Okay. So first of all, given the set of weights, you get an ordinary graph, right? Then
Oh, I
RUV
see.
is the effective resistance between U and V in that graph.
Okay, okay, okay. Thank you.
Okay. Um, yeah. So going back, so this reweighting satisfies these properties, and it's good to know that they can be found using convex optimization. And basically, the second condition, which looks a little bit mysterious, it follows from the KKT condition for this convex optimization problem. And why are these two properties useful? Because then we can, okay, so I'm foreshadowing here a bit, but later on we're going to use these properties to bound the number of hyperedges in the sparsifier. Okay, so this is the sampling algorithm by Lee. Given the hypergraph H, so first you compute these weights C, E, U, V for the clique graph. And then basically you sample the hyperedge with probability proportional to this max of RUV for UV in the hyperedge. And then again, you do unbiased sampling by choosing W tilde to be W divided by P. So it is important to know that this maximum effective resistance is a computable overestimate of the importance of E. And using this fact and Telegrand's generic chaining method, um, Lee showed that the sampled hypergraph H tilde is an epsilon spectral sparsifier of H with high probability with the oversampling rate to be log n log r divided by epsilon squared. So the argument is pretty complicated here, but I think if you're interested, you can go to his paper. And then to bound the number of hyperedges, So first of all, again, the expected number of hyperedges is the oversampling rate times this sum of max effective resistance. And then basically using property one, we can decompose this weight, WE, into the sum of CE and then the maximum, I just renamed it into U prime V prime, nothing changes. And then by the second property, um, when CEUV is positive, then our UV is equal to the maximum. So we can do this substitution. So now the number of hyperedges, you can bound it as basically C times the sum of effective resistance in the reweighted clique graph. So which we know is sort of n. So that means we get the bound n log out divided by epsilon squared. And the extra log out comes from the fact that you need a higher oversampling rate um, to get the spectral sparsifier in the hypergraph case. So are there any questions up to this point? Okay. So at this point, we have seen like two ideas. So the first idea is that um, we can basically just um, do this sampling where we compute a probability to sample each hyperedge. And the second idea is that using these clique graph reweighting, we can sort of reduce the analysis to the ordinary graph analysis using the sum of effective resistance. So for our algorithm, we're going to do something like this, but we need to compute the probability of including the hyperedge that just arrives using previous information. So here's our algorithm. I'm just gonna walk through it. So in the beginning, H tilde is basically all the hyperedges that you included. In the beginning, there's none. And then we also maintain a Laplacian L0. So initially, it's just a zero matrix. And then as the hyperedges arrive, we're going to solve this convex optimization problem for CIUV. So what is going on here is that we kind of assume that there's already a fixed reweighting for the hypergraph up to step I minus one. And then for the new hyperedge, we want to find a optimal assignment of weights in the clique. So this CI, you just want to make sure that this is a convex combination. And then LUV is the edge Laplacian. And then finally, there's this eta IN. So as a regularizer, the point is to give a warm start to the algorithm so that all the eigenvalues are at least eta to begin with. So this once we find the optimal weight assignment, we're just gonna update Li to be adding this. So you can think of it as adding Wi CIUV to the edge UV. And then Li is just the Laplacian of the new graph. And then finally, the sampling probability Pi is basically just the oversampling rate times this ridged effective resistance. So the only difference between this and the effective resistance is now there's an eta I that we add to the Laplacian. And then like just as what we would do for all sampling algorithms, we add the hyperedge EI, with weight Wi divided by pi with probability pi. So are there any questions about how the algorithm goes? Okay, so one thing to note here is that this is actually independent sampling. This is because if you look at um, the Li, it is actually independent of the decisions that we made about the previous hyperedges, whether or not to include. Okay, so so for this talk, I'm not gonna give like full analysis, of course, but I still want to highlight some aspects of how the proofs go. So for the analysis, we want to show two things. The first thing is that the sampled hypergraph is a spectral sparsifier with high probability. And the second thing is that the number of hyperedges in the sparsifier is small. Okay. So for the first one, we're gonna define this eta-ridged energy. So basically, QH of x plus eta times square norm of x. And then we will define this z to be sort of the maximum error between the ridged energy of h and that of the sparsifier h tilde. And for each fixed point x, this is basically a sum of Bernoulli random variables, and then like shifted so that it's unbiased. So there's pointwise concentration, and then using Talleyrand's generic chaining, we bound the basically the exponential moment generating function. And then we can show that for the same oversampling rate, this bound implies that the error is less than or equal to epsilon with high probability. And then finally, we just kind of unwind the definition of ridged energy to show that when Z is M most epsilon, it implies that the sparsifier is an epsilon delta spectral sparsifier. So I'm hiding a lot of things behind this use Talleyrand's generic chaining. Again, if you're interested, you can just go to our paper or the paper that we cited. And for the second part, we have a bound on the number of hyperedges. So basically, this is an adaptation of the analysis by Cohen, Musko, and Pachowski. So basically, we define this phi I to be the log determinant of the Laplacian matrix Li plus eta In. And then in the paper, we show that the growth of this potential function is an upper bound on essentially on the sampling probability. So with this, we can do a telescoping sum. Then we know that the expected number of hyperedges chosen is the sum of pi, which is upper bounded by phi t minus phi 0 times the oversampling rate. And then we can show that phi t minus phi 0 is upper bounded as follows. And then basically just plug things in and then use a trivial bound on the trace of LT. We can conclude that the expected number of hyperedges in H tilde is upper bounded by this, which is what we want. So this is broadly how the analysis goes. Are there any questions? Okay, if not, then finally, I guess I'll mention that the working memory. So one nice thing about this algorithm is that the computation of the probabilities only depends on the Li. So Li is just an n by n matrix maintaining um, like the weights of the edges in the click graph. So that means the working memory is just O n squared. And in comparison, all the offline algorithms, they need memory at least omega m. And this, of course, can be exponential in n. So yeah, that's it. Yeah, so to summarize, in our paper, we got the first online algorithm for spectral hypergraph sparsification. The number of hyperedges that we get in the algorithm is just a log R factor more than the corresponding lower bound for ordinary graphs. And of course, the working memory is an exponential improvement over the offline algorithms when m, the number of hyperedges, is large. So this is a nice, simple result. And also there are a lot of open questions related to it. For example, can we reduce the space complexity from, let's say, quadratic in n to something better like nr? And for the online setting, we're only dealing with edge insertions. What about fully dynamic settings where we can delete edges? So for ordinary graphs, such results exists, but for hypergraphs, this is still, let's see. Okay, I'm gonna get back to the question after finishing this slide. And then some more kind of less directly related questions. First of all, most of the algorithms for hypergraph sparsification, they're sampling based. Can we do something that is potential function based and potentially shave off some log factors on the number of hyperedges? And finally, this one is a bit funny because one big advantage of spectral sparsification for ordinary graphs is that it's actually something that you can check in polynomial time. But for hypergraph spectral sparsification, um, we actually don't know of an efficient way to check that the produced sparsifier is actually a sparsifier. So it's also nice to think about like how to certify this. Okay, so that's it for my talk. And now I'm gonna take questions. I already see there's a question in the chat. So Prashant, you asked, does having exponential working memory help in the online setting? Um, let's see. Yeah, so actually the lower bound, there's no restriction on the number of like the amount of working memory that you have. So as long as you're in the online setting, no matter how much working memory you have, you still need this lower bound like n log epsilon w divided by delta n divided by epsilon squared. Um, so that means our algorithm, it uses just n squared working memory, but the number of hyperedges is already pretty close to the lower bound. Does that answer your question?
Hello, can you hear me?
Yes.
Yeah, I mean, what I meant was like, does having exponential memory help you in the online setting in the sense that, like, are there any results of that sort? Because I don't see how it's immediately useful because you still need to decide immediately for any incoming edge, right?
Well, I mean, at the point of our publication, this is the first online algorithm for spectral hypergraph sparsification. So I'm not aware of any results that uses exponential working memory and deals with the online setting. And even if it helps, the best it can do is to shave off some log factors. Um,
Sure.
yeah.
Thanks.
Mhm.
I had a question.
I'm sorry. I can't quite hear.
Can you hear me?
Okay, now it's better.
Yeah. You said that at every step you're saving the Laplacian of the of like the clique graph, right?
Yes.
But doesn't that make it n cube memory because it seems like the weights will get pretty big by the end, right? Like
So we are
it's still
assuming the word RAM model. That's actually a good question. So we're assuming the word RAM model here. So just one unit of memory per edge per pair of vertices.
I say, but I mean the weights by the end will get something like uh 2 to the n or something. So they'll need n bits or
Yeah, there could
I,
be some dependence on like W if you want to analyze the number of bits.
okay. It seems like there's a dependence on n though, not this w. That's what. But uh, for example, if your input's the complete uh, say the complete hypergraph,
Mhm.
by the end, the elements like the weights in your Laplacian will be something like 2 to the n in value. So you'll need like n bits to store them.
Yeah, if unweighted,
Right?
yes.
Yeah, just for the unweighted case, that makes it yeah.
Mhm.
So I'm not sure if the word RAM model is like seems weird to use the word RAM model here.
Yeah, but I think in any case, the dependence. So suppose the weights are not like exponentially small or large for each
Yeah.
hyperedge, then I think the dependence on the number of hyperedges will still be improved. Like instead of linear in M,
Yeah.
you get something logarithmic.
Yeah. Okay. Yeah. So I feel like it'd be like n cube or something, not n squared, but I guess it's still exponentially better than the other stuff.
Yeah, it depends on how you interpret the results.
Yeah. Okay. Thanks.
Mhm. Yeah. Are there any other questions?
If not, argue is.
Thank you.
Thanks, Alex.
Yep. Thanks a lot.
Yeah, thanks for coming. It's actually 2:46 a.m. here.
Oh.
You'll be partying hard.
Don't do that every day.
It's a one-off for you guys. All right, then. Let me stop the recording.